This is why you'll never become a true senior engineer using Python. Sure, you can write clean idiomatic code, follow solid principles, and implement design patterns using high-level abstractions. But the harsh reality is this. If you don't understand the underlying mechanics of the system, memory allocation, data alignment, and runtime behavior, you're trying to anchor a skyscraper on shifting sand. To all the Python developers out there, if you can answer the next 3 questions without ChatGPTing the answer, I'll be impressed. What causes a segmentation fault? How many bytes does a float take up in memory? What is temporal or spatial locality? These are things Python conveniently hides. It manages memory for you, automatically running garbage collection in the background. To become a true senior engineer, you need to peek behind the curtain of abstractions. I'm going to give you a glimpse into C, a language where you take full control of memory management. And at the heart of C's power lies malloc, the function that lets you dynamically allocate memory. There are no safety nets, no garbage collectors, no invisible optimizations. In the C standard library, malloc is responsible for allocating memory on the heap as requested by your program. When you call malloc, it takes the number of bytes you want to allocate, finds a block of free memory on the heap, and returns a pointer to that block. The memory is dynamically allocated, which means you get to decide how much memory your program needs during runtime rather than at compile time. But what's happening inside malloc? When you call malloc, the system reserves a chunk of memory on the heap, a portion of memory that persists for as long as you need it. The heap is different from the stack, which is automatically managed by the system to handle temporary data, like function call frames. The heap allows you to dynamically allocate and free memory as needed, giving you more control. But C doesn't know the types you're working with, so when you allocate memory, you must specify the number of bytes needed. This is where size of comes in handy. It's used to determine how much space you need for a particular data type. For example, if you want to allocate memory for 3 integers, you'd use the following expression. Here, size of int ensures that the correct amount of memory is allocated based on the system's definition of an integer size. This makes your code portable because it adapts to different system architectures. Since malloc returns a void pointer, a generic pointer, you often need to cast it to the appropriate type. For example, when allocating memory for integers, you cast the returned pointer to an int pointer. One of the most important things to remember when using malloc is that if you try to allocate more memory than the system can provide, malloc will return a null pointer. This indicates that the allocation failed. And once you're done with dynamically allocated memory, it's your responsibility to free it using the free function. Failing to do so will result in memory leaks, which can severely affect the performance of your program over time. Best practice is to not only call free, but also to set your pointer to null to avoid using memory that has already been freed. Okay, but at an even lower level, what really happens during malloc? At its core, malloc operates within the heap, a memory region dedicated to dynamic allocation. To efficiently manage this space, the allocator tracks used and free blocks. It does so using a free list, a linked list of memory blocks that are available for allocation. Each free block contains metadata, which includes the size of the block, which tells malloc how many bytes the block can hold, as well as pointers, which link the block to the next and previous free blocks in the list. When you call malloc, the allocator searches the free list for a block large enough to satisfy your request. One of the most critical tasks handled by malloc is alignment. Alignment is the key reason why malloc can't simply return any block of memory. Modern processors are optimized to read and write memory when data is aligned to specific boundaries. For example, a 64-bit system often requires memory to be aligned to 8-byte boundaries. And misaligned memory accesses can lead to inefficient CPU operations, for example, multiple fetches instead of one. Some architectures may even throw hardware exceptions if memory is not properly aligned. So how does malloc ensure alignment? First, it rounds up the size. When you request n bytes, malloc rounds the size up to the nearest multiple of the system's alignment. For example, if you request 13 bytes on a 64-bit system, malloc will actually allocate 16 bytes to satisfy the alignment constraint. And second, it will align the pointer. The allocator adds padding to move the pointer to the next aligned address. And this is done using a bitwise operation. In practice, you don't need to worry about alignment in typical usages of malloc because the allocator handles it for you. However, if you're working with custom allocators or certain system-level programming, alignment can become important. It's also important to note that unlike calloc, malloc does not initialize the allocated memory, which means that the memory contains arbitrary data, whatever was left in those memory cells. Okay, but how about the edge case where there isn't enough free memory in the heap to satisfy your request? In this case, malloc may request more memory from the operating system, and this is done through system calls such as mmap or sbrk. SBRK increases the program's heap by a specified number of bytes and gives malloc additional space to allocate from. Let's say before, the heap ends at address 0x1000. After calling SBRK and passing it 4096, the heap extends to 0x2000, which provides an additional 4 kilobytes of memory. On modern systems, malloc often uses mmap for large memory allocations, for example, over 128 kilobytes. Mmap maps a file or device into memory, but when used with special flags, it allocates anonymous memory directly from the OS. So the memory is not part of the program's heap, which is managed by the allocator. Mmap returns memory that is directly allocated from the OS's memory pool. It's important to remember that this allocated memory is distinct from the heap and does not go through the standard heap management mechanisms, which is useful for large allocations that are too big to be efficiently handled by the heap. And it does not use the heap's free list or block management mechanisms. Understanding how malloc works and the low-level memory handling it involves provides a lot of insight into systems programming and helps you write more optimized and performance-conscious code. If you learned something new today, please drop a like on this video and subscribe for more programming and software engineering content. As always, thank you very much for watching and happy coding.